Okay guys, welcome to our video 2, which is our second type of solving. And this is going to really get down to the definition of like a square, right? Something being squared. So actually I just want to cover this up now. I just want to look at number 1 with you. So number 1 says if I have x squared minus 81, notice this is also a quadratic function, right? If I think about my ax squared plus bx plus c, it looks like I just have the x squared and the negative 81. So it looks like I just have my x squared and my c, right? There's no a, it's like a 1 is in front as the coefficient. And that means that there's a 0 for b. So this is like also a quadratic equation. It's just a little bit smaller. It's a little bit less complex. And if I want to solve for x, what's kind of nice about this is if you add 81 to both sides. I'm telling you that x squared is 81, and I bet you could tell me what squared is 81. I bet you said that. I bet some of you remembered this guy here. Remember if you do a negative 9 times a negative 9, two negatives make a positive 81. So this idea is x is the square root of 81, right? We're square rooting, and if we're doing that, if we think about square rooting both sides, right, you can think about it as like the positive and the negative square root of 81, because it was something times itself, and that x could have been a negative 9 or a positive 9. So this big idea that we're using here, the way I like to think about the second type of solving quadratic equations, is that we're really just using squaring and square roots. So we're solving using like the definition of squaring and square roots. Okay, and then ignore this for now. This is going to come up in a little bit. Let's just focus on using ideas of square roots and squaring. Right, that's like the big idea we're using, is like what it means to square something and how to undo that squaring by a square root. Trying number 2. Number 2 is a little bit trickier. There's a little bit more going on. But let's think, okay. The last problem, I got it down to something squared equals a number, right? This was kind of the sweet spot, getting it down. If I'm viewing this kind of looks like something squared minus 81 equals 0, right? So I'm going to try and do the same thing. I'm just going to add 81 to both sides. And then I've got x minus 4 squared equals 81. Let's think about if we undo that, right? This is kind of like our undo step, where we square root both sides, right? The square root of x minus 4 squared, that is just going to kind of give us back what's underneath, right? X minus 4 squared. So unsquaring it or square rooting it gives us back the original. And it could either equal a 9 or x minus 4 could equal a negative 9. Because a negative 9 times a negative 9 is also a positive 81. So from here you're going to do your solving. Just kind of add 4 to both sides. Looks like x could have been a 13. Add 4 to both sides. And x could have been a negative 5. If we double check these, right, you always want to double check at the end. The first one was kind of an easier one, so we didn't really need to do so much of a check. Let's check that out. Make sure that it looks good. If I plug in a 13, 13 minus 4 squared, that's going to turn into 13 minus 4, which is 9. 9 squared is 81, and 81 minus 81 is 0. Double checking the number negative 5 as well, right? That becomes a negative 9 squared. Negative 9 times negative 9 is 81. So it looks like both of them check out, right? We wanted 81 minus 81 to get 0. Let's try one more, and then maybe I'll have you try the last one on your own. Yeah, so we've only got a couple more. So this next one has a little bit more going on. And this next one, number 3 and number 4, the idea I want you guys to think about is that we're isolating by undoing. So we're trying to isolate, in both of these, your goal is to isolate the something being squared and have it equal just a number. So we're trying to isolate this stuff here. And we're trying to isolate this stuff here. So we just need to think about how to get rid of everything else. So think about it like a regular solving equation, right? We want to get this down to the point where we can just be able to say if something squared equals a number, right, I could square root it. So with this one, we're going to be moving some stuff around. And I do want to point out, like with all of these look a little bit different, right, from the ones we started with factoring. If I was to just multiply stuff out, right, x plus 1 times x plus 1 plus 5 equals 133, right, that becomes 2 times, if I do my foiling, x squared, there's 1x, there's another x, so I'll put 2x plus 1 plus 5 equals 133. If I distribute the 2, it becomes 2x squared plus 4x plus 2. I'm just going to brush that up a little. It looks a little messy. And if I move this over to the other side, it becomes minus 128. And then you could combine these two for your constant. But notice if you do all that distributing, it does actually get to the point where it looks like that standard form of a quadratic. If we look at what this actually reminds us of, this should remind you guys of, like if I focus on moving this over, right? This should remind you of what we saw with our transformations. If I think about this as a transformation, just kind of big picture, right? You should be able to see like a left and a right shift from this number, the up and down shift from this number, and this number tells you the stretch factor. So equations that are in kind of what you think of as the transformation form, the fancy term for this form is that this is vertex form, because it gives us really clearly, we can figure out where that point is based on the left, right, up, down shift. So anything that's more in this structure is kind of attuned to solving with square root ideas. So I just wanted to point that out, just because I think that's a valid thing to take a little bit of time to think about. So kind of keeping in mind that these have a very distinct structure from the previous ones, right? Our previous page that we were doing was always in standard form, all multiplied out. That's typically how factoring problems are given to you. This one was in the form that you can clearly see the transformations of the function, and you can clearly see the left, right, up, down. And we typically call that form vertex form because it tells us where that point is based on the left, right, up, down shift. So let's think through number 3, and then I'll have you try number 4 on your own. We want to think about how to isolate that whole thing in the box, right? First thing I have to undo is adding and subtracting, so I'm going to minus 5 on both sides. 2 times x plus 1 squared is equal to 128. And then I want to divide by 2. Think about it like if it were just an x instead of that whole big mess, right? If it was just 2x plus 5, you would first do the minus 5, then divide by 2. So now I've got 128 cut in half. Let's see, that's 50, that's 64. And then from here, I can use my definition of my square root and square root both sides and say that x plus 1 is either equal to 8 or x plus 1 is equal to negative 8. Remember on this side, they're undoing each other, right? If you square something and then square root it, you're back to where you started with. And then from here, you're going to subtract 1. Subtract 1. Subtract 1, and x is negative 9. And if I were to plug that back in, right, as 7, 7 plus 1 is 8, 8 squared is 64, and then from there you've got 64 doubled, it's 128, added 5, and that gives you 133. Same thing should work for negative 9, right, it just becomes a negative 8 when you plug it in to negative 9 plus 1, and then that negative number squared is a positive. So why don't you try number 4 on your own? I'm going to pause the video and try it on your own. Unpause when you're ready to check. Okay, so this one worked out a little funny, right? When you subtract 71 and put that together with the 8, you get negative 63. Dividing by negative 3, you get 21. And then the weird thing is we don't have anything that we can square root 21 as perfectly. So because of that, the way I would kind of be inclined to solve this is just to leave it as the square root of 21. Because notice you can't simplify that square root at all. I can't break it down into something times the perfect square. So I'd probably just write it as -9 plus the square root of 21. Same kind of thing over here. Or -9 minus the square root of 21. If you wanted, you could write that as -9 plus or minus the square root of 21. If you want to put them together, that's kind of a compact way to, that's kind of a compact way to put those two options into one with the plus or minus. So that one's just a little trickier because we don't have a clean square root. I would say to always leave it in terms of a square root. If we had something more like the square root of 50, right? Remember, you want to break that down into 25 and 2, and then we would call that 5 times the square root of 2, right? Because we always break it down where you are multiplying them. But in this case, this one did not simplify. I just want to point out that you would if you could. There's one last thing I want to talk about, and this is kind of like a side topic that's somewhat connected to this. So this might be something that we talk a little bit more about tomorrow in class. I want to compare and contrast these. When does y equals x squared minus 9 equal 0, and when does x squared plus 9 equal 0? If you think about our shifts, right, you should be able to tell me, what does the minus 9 mean? Which way do I move and how many? You're probably guessing, 4, 5, 6, 7, 8, 9, that it means that you shifted down, and you would be correct. So you've got the down 9, and it kind of looks like this. So when does it equal 0? When does y equal 0? It looks like we're going to have 2 points. So let's see, when does x squared minus 9 equal 0? I'm going to use my squaring ideas and add 9. And x squared is equal to 9. So either x is 3 or x is -3, right? 3 times 3 is 9, -3 times -3 is 9. Let's think about, when does y equals x squared minus 9 equal 0? When is the output? When is y equal to 0? If I think about this one is going to be up 9, whereas this one was down 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. So, what do you guys think about this one? Think to yourself, what would this one be in comparison? This one's going to be a little weird. Let's try it out. If I follow the same steps as before, I've got x squared is equal to -9. So, at this point, what I want to connect this to visually is if you get the square root of a negative, right? Normally we can't do anything with that. And the reason why you'll see is because there are no x-intercepts, right? That's what we're generally looking for. There is a way to write it if you want to write it mathematically. We do have a way to write it in a nice form. So we would say x is the square root of -9, right? Or x is the opposite of whatever the square root of -9 is. There is an idea in math, and normally we spend a little bit more time, but with e-learning, I was trying to figure out how to put this in a thoughtful way without going too in-depth. There is this idea in math of something called imaginary numbers. And that's when you have like the square root of a number, like the square root of -1, where you've got that negative sign. And what mathematicians have done is they've defined the square root of -1 as I for imaginary, because it doesn't exist. And so what's nice about that is if I have the square root of -9, I can write that as I. So if you think about x as the square root of -9, right? If I just kind of separate the square root of the negative from the 9, right? I can say, okay, that's an I, and I know the square root of 9 is 3. So I can say that x is 3i, is how I could write that. I could also rewrite this other one, right, the same kind of way. So x in this case would be, we've got that negative sign, -3i, because I would be separating this into the square root of 9, which is 3, and the square root, let me just rewrite that, and the square root of -1, which we're calling an I. And so the usefulness in my mind of this is that it makes a connection to why we don't have x-intercepts, because they're imaginary. And this is something that I'm sure you're going to be a little bit unsure about, so let's talk about this together on Thursday. See you guys then.